depending on the substitute. So let's start with acetic acid, which is has a pK value of about 4.7. And it is an acid, therefore it, in aqueous system, it's going to donate the proton. Water picks up that, becomes an oxonium ion, and the anion that is formed, which is the conjugate base, is resonance stabilized. We know all of that. Now, depending on what is here, that would, if it stabilizes the anion better, then that would be a stronger acid. If it destabilizes the anion, that is going to be a weaker acid. So it's a simple issue. And you can predict that if you attach an electronegative group So if you attach an electronegative element, depending on how efficiently it pulls the electron, it will make it a stronger acid because the anion is stabilized better that way. So if you attach a halogen, it clearly will become a better acid. And the pK value drops than acetic acid. And so most of the time that argument essentially holds most of the acidity strengths because typically the acetic acid and the other carboxylic acid have a range of typically 4 to 5, but it could be even better. It could be, if you attach 3 chlorines, for example, it drops below 1. Okay. So it's a fairly straightforward argument. You should be able at least not predict the number, but you can figure out the relative strengths. And later on, we'll try some problems to make that argument. Same thing with the others, like benzoic acid is a slightly better acid than acetic acid because of the presence of the ring system, which is kind of an electron withdrawing, and therefore that makes it a better acid, but not by significantly extent. Better acid than acetic acid. Okay. But then again, if you put an electron withdrawing group, for example, if you So now predict the acid strength of these 3 different acids. You have para-chloro, para-nitro, and para-methyl. Okay. Which is the weakest acid? The methyl. Because it's donating electron and therefore making the anion less stable. So this is the worst of the 3. Okay. And this is the best. Why? Because the nitro group, if you think about it, has 2 oxygens attached to the nitrogen, and the oxygen can pull actually the electron much more efficiently, and therefore nitro is far more electron withdrawing than chloro, and therefore this is a best acid, and chlorine is somewhere in between. So it's predictable what the strength is. You may not know the number, but you should be able to predict these effects. And we'll go through some problems later on. Don't spend too much time on that. Yes?
Sorry to be back. Does that just follow the order of deactivating? That was order in the bottom. Like
Correct. More deactivating groups are more electron withdrawing. So that analogy, yeah, can be used as well. Now, if you take an acid, carboxylic acid, and treat it with a base, like sodium hydroxide, we see that that's going to form a molecule of water and a sodium salt. And we can also see that this is a pK value of 4.7 or so. Water has a pK value of 16. Therefore, this is a stronger acid. And between the bases, sodium hydroxide is a stronger base. So the anion, we do it by reverse relationship. Stronger acid is a weaker base. So therefore, carboxylic acid with a base, as long as the base is as good as sodium hydroxide, can form a salt. Now, this has a completely different significance from other aspect as well. Let's consider you have a long chain and you form a salt like that. Then we see that the salt part, which is actually an anion-cation relationship here, so this is extremely polar, and therefore they are hydrophilic. Okay. So it loves water because water is polar. On the other hand, the long hydrocarbon chain that you have is actually hydrophobic or lipophilic. Okay. And because of these dual characteristics, what happens is that if you throw this in water, what may happen is that you have a polar group, such as this one, the polar head group, and then you have a tail, which is very, very hydrophilic. So what they do, therefore, is to avoid water because it hates water, and about 50 or 100 molecules then aggregate like this.
Looks like sperm.
Okay. And what happens is the surface, this is the water part, the head groups actually expose themselves to the water molecule because they're hydrophilic, and the long tails would avoid water, and so they aggregate and form what we call a micelle. And the micelle has a major significance because soaps and detergents are essentially form micelles. They have long fatty chain of hydrocarbons and a very polar head group, which could be sulfate or carboxylate and so forth, which is a hydrophilic thing. And so what happens is if you have grease on your hand and you take soap and you rub it, what happens is the grease goes in the, which is also hydrophobic, it goes in the middle, okay, because that has the fatty chain that can trap it, and then you wash it with water and that goes away. And that's essentially the action of soap. Soap and detergent work essentially this way. So that is really the action of soaps and detergents, how they work by this arrangement of the hydrophilic head group and hydrophobic tails of these. And I'm going to skip the next couple sections as I already emailed you, the dicarboxylic acid and carbonic acid. But you already know about carbonic acid, right? This is all the soda, carbonated beverages. Carbon dioxide is not very soluble. It forms a very small amount of carbonic acid reacting with water. And the rest of the carbon dioxide essentially is trapped there. And so when you open up the soda can, it just starts bubbling up. But it does have a reasonably low pH. If you check your pH in a soda can, you'll see about 2 or 2.5.
That doesn't sound safe.
Because of the carbonic acid. Anyway, we'll move on to the reactions of carboxylic acid and preparation of carboxylic acid. Now you already know about the synthesis of carboxylic acid. And these I'll not go through. There's a table that summarizes this, go over that. But there are two new methods that I'm going to introduce. One using a Grignard reagent. Okay, so the Grignard reagent, the way it's being used is like you can use a Grignard reagent with carbon dioxide. So let's say if you have metal, magnesium chloride, say you made from metal chloride, and then you treat it with carbon dioxide, the reaction is again very similar, that the methyl group attacks the carbon and then it generates the OMgCl, which can be hydrolyzed in the presence of acid, and then you pour the corresponding carboxylic acid. So this therefore gives you, just like you use formaldehyde to add a CH2 group to an alcohol and extend the chain, you can do the same thing. Whatever group you have, let's say you have 1, 2, 3, 4 carbon chain. If you want to extend to 5 carbon and make it a carboxylic acid, you can very easily do that. Use carbon dioxide in ether and then hydrolyze that. Then you are going to add another carbon, 2, 3, 4, 5 now. So an extra carbon is added now. Okay. So this is a common method of using carbon dioxide to introduce a carboxylic acid group to an alkyl halide or similar type of compound. The second method is hydrolysis of cyanide. the hydrolysis of cyanide actually allows you to also introduce a carboxylic acid group. So frequently you can use a standard method, like let's say if you have a chloride, in the first step you use sodium cyanide. So you displace the chlorine with the cyanide, and then you hydrolyze that using aqueous acid. So H2SO4, water, and then heat. That would hydrolyze the cyanide to a COOH group. So that's another method that anytime you can make a cyanide, you can carry out this type of transformation. And the standard method is using a strong acid, but you can also use base. You will see some of the examples where KOH is also used. Water and heat. They also will do the same thing. Hydrolysis of cyanide.
H2O, KOH and H2, you're talking about the second step, right? The first step always has to be NaCN and DMSO.
First step means treating the cyanide, or
No, first one. Yeah.
Yeah, well, you have to make the cyanide first.
Okay.
Okay.
Okay, yeah.
So let me give you another example. Okay. So let's say you can have even a carbonyl compound. Let's say you have a ketone. And in the first step, then you treat it with sodium cyanide. Okay, and then you hydrolyze that. Then you get a cyanohydride, right? So and then you hydrolyze that. Now, basically the difference between this step and this step is that this is a relatively weak acid, and this needs a somewhat stronger acid condition, and you have to heat it also, okay, in order to hydrolyze the cyanide. So now, this is being hydrolyzed to COOH, and this one remains there. Yeah?
Question about the previous page, the carbon dioxide reactant. Don't you need to make it a Grignard reagent before you can do the carbon dioxide diethylesis?
You can also do that, right? In other words, the Grignard reagent essentially, then you have to use carbon dioxide. You can make, let's say you have an alkyl halide, you can convert it to that Grignard and then treat it with carbon dioxide and treat it with acid.
Okay.
That will also introduce that.
So you can just go straight from the halide with carbon dioxide diethylether instead of making it a Grignard reagent?
No, you have to make the Grignard first.
Okay, that's what I'm doing.
Yeah.
Okay.
So, again, the reactions of carboxylic acid, you have seen quite a few of those. Now, for example, making the acid chloride by treatment with thionyl chloride, you have seen the lithium aluminum hydride reduction to the corresponding alcohol, and also the esterification. Esterification is particularly important. You have seen that before, but let's go over that again. just to review the material and understand the mechanism better. So let's start with acetic acid. And let's treat it with ethanol. In the presence of acid. Then you would expect this to form the ester. Okay, so now the way this reaction proceeds is that in terms of the mechanism, the very first step is the acidification of this, and therefore the oxygen picks up the proton. So it's a proton transfer reaction at the very first step, forming the protonated form of the acid. Therefore, now you can write the resonance structures. One structure will have a positive charge on the carbon. The other one is this one where you have the positive charge on oxygen. Therefore, this is really set to undergo an attack by the ethanol. So the ethanol attacks, forming this. Okay. Next step is a reaction with another molecule of ethanol to remove the proton. Therefore, now you form next is another protonation of one of the hydroxyls, and you use another molecule of water, oxonium ion essentially, to form now this is set to undergo a rearrangement to eliminate a molecule of water, giving you this. And the next step would be removal of this proton.
Gosh.
So another molecule of ethanol or water going to pick up this proton and generate the final product. So this is essentially the mechanism of this process. Now, notice one thing. Let's start with marking one of the oxygen of the ethanol. So this is the one, okay. Then in the subsequent reaction, this is still the oxygen, and this oxygen is here, and then this is still here, and here, here, and here. Therefore, in fact, this type of experiments were done in which you start with a normal oxygen 16, and in the ethanol, you introduce an oxygen 17. And when the ester is formed, always you will see that one of the oxygen of the ester will have the O17. This one is O16, this is O17. And that's how we know this is the mechanism that is operating in the process. So in case of ester formation, the oxygen is not this oxygen, but the oxygen that comes from the alcohol. So one of the oxygen in the ester will have the original carboxylate oxygen, and the other one will come from the alcohol. Okay, so that's as far as the mechanism of this reaction is concerned. Now the ester formation can also happen intramolecularly, and those molecules are called lactones. Therefore, if you have the alcohol group and the carboxylic acid group in the same molecule, they have the ability to therefore undergo the reaction intramolecularly. Right? So this one can attack, and essentially then, under acidic condition, this is going to cyclize, and because you have three so this is called a lactone. And yes.
So acid can be like H2CO4, SO4, instead of acid. Yeah.
You mean the acid
Yeah.
to be used?
Any kind of acid.
Yeah, any kind of acid, as
Okay.
long as it's a certain pH that is usually recommended, and typically as long as the pH is less than 1 or so, that would be fine. Okay, so you can add aqueous sulfuric acid or hydrochloric acid. That should work. So in this process now, depending on what kind of molecule you have, you can carry out this type of reaction, the intramolecular ester formation. There are two other sections that I need to go over, very short sections, the decarboxylation and then the spectroscopy part, which we'll do Monday. Let's go over some practice problems that we have, both from chapter 17 and chapter 18. Okay, so these are reasonably straightforward problems. In case you don't have it, I have copies of these. All right. The problems are actually quite straightforward, but I want you to take you over so you recognize where to focus. Okay. 1731. These are from chapter 17. Okay. So the way to look at this problem is that which one is the reactive functional group. And when we look at this, we can see that you have an aldehyde group here, okay, and you have a glycol, the alcohol. So they are going to react and form initially an hemiacetal and then an acetal. So in this case, therefore, since there's no space here, I'm writing on the other side.
Can you scoot it?
So leave this rest of the molecule exactly like the way it is. So you rewrite everything. Okay, so rest of the molecule I just left it intact. And so now this carbon is going to form an acetal, therefore these two oxygens would be attached to it. So the hydrogen remains there, but the two oxygens will be attached. And now between the two oxygen we have 1, 2, 3 carbon. So therefore 1, 2, and 3. This is going to be the product of this, essentially forming an acetal. Second reaction likewise, focus on the reactive group. The reactive group is again the aldehyde, and that's going to react with an amine. This is the amine, NH2, and it's going to eliminate a molecule of water and form again, we leave everything intact. And this carbon now is going to form a double bond with the nitrogen, and the molecule of water is taken out, and nitrogen is attached to an OCH3 group. So this will be the product. And the next one is again very similar. You have the NH2 here and the CO here. Those are the two functional groups that's going to react. So N connected to another nitrogen and the two methyl group. Now this reaction is the reverse of the acetal formation. This is an acetal. So now under aqueous acidic condition, this is going to be hydrolyzed. So you recognize which carbon was aldehyde before. This is the one, right? So this is going to form and obviously the other product would be the ethylene glycol. Okay. Next one is formation of cyanohydrine. Okay, I'm writing on this side now. So the cyanohydrine again is, you need to focus here, the Cn minus is going to attack the carbonyl group, and that would form the ONA first, which would be hydrolyzed by HCl, and therefore this would become COH, CN, and there's a methyl group here. Okay, the next one is again similar to the previous one, except that now we have a secondary amine. Therefore, it's going to form an N-amine. It initially forms
Could you scoot it over, please?
so this is going to form a C.
Could you move the paper on the a little bit? Yeah, thanks.
So this is going to be eliminated as a molecule of water. You form the N, then you write the rest of the molecule, and you have a methyl group, this is formed first, okay? And now you cannot eliminate a molecule of water between these two because the nitrogen will be positively charged, which is actually an intermediate form, and then it's going to actually form the double bond between the next carbon. So C double bond CH2 and N. So this is an enamine. And so this is what is formed. And this one is a very straightforward. Rather than oxygen, well, two oxygens, you have sulfur, but it will still form the same thing here. So it's going to form going on the other side. So this is the carbon, and now this is joined with the two sulfurs, sulfur and the, sorry, let me erase that. You have oxygen and a sulfur, and in between you have two carbons. So this is going to be formed. Ignore this, whatever. So these are fairly straightforward reactions. All right, let's see. Going to the next page. Let's try one or two of this. This is now, again, these are cyclic molecules, but you have to know when to break it in order to form the corresponding, because this is a cyclic hemiacetal or cyclic ketal. These are really open chain compounds when you break it. Okay, but where are you going to break it? This one, you gotta break it between the carbon that has the OH group and the oxygen, right? So you have to break it here. If you break it there, this is being formed through, this becomes OH, right? And this one is CHO, right? So the hydroxyl group now, that was where that carbon was the aldehyde. Here, you gotta recognize where the carbon that has the carbonyl group. And again, this is the carbon that is attached to two oxygens. And therefore, you know that you can redraw this so that you have this oxygen becomes OH. This other one, this is also OH. And this is where the carbonyl was. So you need a little practice to figure out which one. You need to recognize that this carbon that is connected to two oxygen, that was the originally keto group, and the oxygen really was coming from the alcohols. So the two OHs are there. So you should be able to do all of the other problems. It's very similar to this. Okay, as long as you recognize the carbon that is really important.
Could you try D, maybe?
What?
Could you try D,
D.
please?
Okay, so D is actually easier than C.
Not.
D, you see again, this is the carbon that is of, we should focus to. Okay. And therefore, that's the one you had the carbonyl group. So rewrite exactly like the same way. Okay. And okay, so this was OH, and this was also OH. and the carbonyl was here. Rest of the molecule remains the
Okay.
same. CH2OH, OH, and this is CH2, CH3. Got it? Okay. All right, so let's move on to now chapter 18 problems. Try a couple of them. This is the one we kind of discussed today, where identify the more acidic compound between the two. So A is asking you about CH3, CH2CO2H versus CF3, you have two CH2s. Therefore, the CF3 going farther away, and therefore will have less influence, right, on stabilizing. Therefore, this is the more stronger acid. Same way, you have 3 carbons, but in this case, you have a triple bond. And as you know, double bonds are shorter than single bond, and triple bonds are shorter than double bond. And so they get closer, and also the pi bond can transmit it much better. Therefore, this will be actually have more influence on that, stabilizing the carboxylic acid. Now, between benzoic acid and cyclohexane carboxylic acid, the effect would be the electron withdrawing effect of the benzene ring. Therefore, this is a stronger acid. Between these two, this one has a bunch of fluorines, this one has none. Therefore, again, fluorine has the electron withdrawing effect. This would be stronger acid. Between these two, this is all the fluorines are separated by the benzene ring. Therefore, this is a stronger acid. Likewise, in the next one, the oxygen is right next to the carboxyl group here, and here it's separated by CH, and therefore this is closer and therefore stronger acid. Between these two, you compare nitrogen with oxygen. Oxygen is more electronegative, and therefore this is a stronger acid. So it's fairly straightforward to actually predict the better acid of the two. Okay. And something else here. Oh, you should be able to do all of that.
Oh.
All right, I gave you some practice problems. Okay, try them during the weekend, and we'll